Hello, everyone. Welcome to SimScale's webinar on enhancing the hydrogen supply chain through cloud-native simulation. I'm your presenter, Kanchan Garg. I'm a product manager here at SimScale, where I'm responsible for our company's strategy and development across industries like rotating machinery, industrial equipment, and flow control. And joining me today is my colleague Ajit Jayakumar, who is a senior application engineer at SimScale, and might I say, with a very strong and diverse experience in supporting our customers across industries. Hi, Ajit. I'm very excited to be here doing this webinar with you. How are you doing?
Thanks, Kansan. It's always nice to do these webinars where we can get some great conversations going on. Happy to actually present this, and also a warm welcome from my side to the audience.
Thank you, Ajit. Before we kick off, just a gentle reminder to all of you that your mics will remain in mute during the course of the webinar. If you're facing any technical difficulties, please reach out to our webinar coordinator using the chat option. And for any questions that you would like us to address at the end of the webinar, please use the questions panel. So what are we going to cover in this webinar? I thought it would be a great idea to begin with getting a holistic view of the challenges that the hydrogen industry faces today, because that helps us build the context of how simulation, and specifically how cloud native simulation, can really help in advancing hydrogen technologies. SimScale has a lot to offer in this respect, which is what we will go through in detail as we look at the different use cases and case studies, for example, like thermal management of a hydrogen fuel cell, storage tank, etc. And definitely, as promised, we will have some time for question and answers at the end. So in terms of challenges, definitely it starts with hydrogen production, which needs to be economical, which needs to be scalable. And I talk here about green hydrogen production, but there are lots of other new technologies also being explored, like using sewage water for producing biohydrogen, and or using excess nuclear power to produce pink or yellow hydrogen. So there are a lot of conversations that are going on, and central to all of it is how can we scale production in an efficient, economical manner. And next in the story is how hydrogen can be more efficiently stored and distributed. It's a difficult element to handle in terms of its density, in terms of its flammability. And an interesting tidbit here is that right now, about a lot of hydrogen transport happens using truck systems as liquefied hydrogen. And 30% of the energy in liquid hydrogen is actually lost either in the form of losses to the environment, or simply in the process of converting gas to liquid and then back to gas for utilization. I mean, what a waste, right? So there's definitely a lot of uh, room for efficiency improvements here. And finally, from a utilization perspective, I'm talking about the transportation industry here, but this is also applicable to all the other industries where hydrogen can be used, like aviation. And there is a lot of innovation happening here in terms of improving storage and fueling infrastructure. There's a lot of conversations about whether fuel cell electric vehicles are better or hydrogen powered internal combustion engines are better. But irrespective of the different technologies that are being explored, irrespective of the pros and cons of each of these technologies, one thing is clear, that hydrogen is very central and very important in the whole energy transition story, right? And there are thousands of components and systems and processes that need to be either developed from scratch or optimized and retrofitted to be able to advance this technology. And that's really where scalable, fast, and accurate simulation can really help, because a lot of this prototyping, a lot of this innovation can be done virtually. And that's where SimScale comes into the play. As you can see here, SimScale understands the specific pain points of the energy industry, and we have experience in supporting engineering teams across similar industries in innovating faster and in exploring a bigger design space that enables them to innovate and create products in a reliable and safe manner. And how do we do this? I will not spend a lot of time because I think at least some of you are already familiar with SimScale, but I just want to touch upon the salient differentiators of SimScale with respect to other simulation tools. So we are the world's first truly cloud native simulation tool, which means that you can start simulating just from about any browser that you have. You don't need any hardware or VPN or remote desktop connections. And within, behind this one platform, you have a broad range of physics that can be accessed. So basically, you can come in with your model and leave with a multi-physics design decision about your product. And because we're on the cloud, what we also offer is a very Google Docs style type of collaboration. For example, you can share your projects, you can have your colleagues who might be sitting in a different country, different time zone altogether, come in, view your simulation projects, and weigh in your design on your design decisions in real time. So no more waiting time to create detailed presentations, go back and forth, discussing, what next steps to be taken in the design process. And very recently, we released our AI trained modeling, which sits right next to our physics based predictions. And the most important thing, which I also touched upon in my previous slide, which is very relevant for the hydrogen industry innovation, is the scalability of simulation with SimScale, because there's practically no limits to the simulation size or the number of parallel simulations you can do or the storage capacity. And all of this is handled by SimScale. You don't need any IT intervention, you don't need any HPC orchestration. Everything is built into one platform. And behind this powerful platform is equally powerful physics modules that are very well validated with industrial problems across customers, as you saw in some of the previous slides. So you can basically come in with your product, the CAD model of your product, and do a flow analysis, thermal structure, electromagnetic analysis, and understand in a holistic sense how this product would behave in the real world. Now that was about SimScale, right? But I'm sure all of you are interested to know what SimScale has to offer specifically for the hydrogen industry. So going back to the different steps in the supply chain, right? Whether it is in the production stage where you're looking at an electrolysis plant, which will also have some filtration systems, desalination systems associated, or you may have storage tanks and pipelines that need to be retrofitted for transporting hydrogen to the point of use, your refueling stations, or your actual electric vehicles which are being powered using fuel cells. All throughout this supply and utilization chain of hydrogen, SimScale has something to offer. SimScale has use cases that will help you design components, systems, and processes and optimize them, make them more efficient by leveraging early simulation early in your design process. So you're not leaving your design decisions right at the time when you want to start investing in developing the prototype. So that was in a nutshell what SimScale has to offer. And now I think we should really get into the details of it. We have picked a few case studies across the supply chain of hydrogen to try and explain, to try and demonstrate how SimScale can be applied and utilized, and what features you have, and what's the kind of simulation output and design decisions that you can make. And for this part, I will hand over to Ajit, who will take you to the platform and give you all the necessary details.
Thanks, Kanchan, for the wonderful breakdown of the design challenges in the hydrogen supply chain and how simulations can mitigate prototyping cost, for example, and also predictive maintenance, and also opening up new design possibilities, as you mentioned at the last slide, right? And as Kanchan mentioned, we'll be looking at 3 specific use cases relevant to hydrogen industry, and the aim of these use cases is to actually get a feeling of how simulations will help improving the efficiency, and also alongside we'll talk about like how you can set up these simulations and extract the results that you are interested in actually using it for informed design decisions, right? So for the next 20 minutes we'll explore together these 3 use cases. based on a tank filling case, a seals that is used in hydrogen industry, either for storage or transport of hydrogen. And lastly, we'll also look into the thermal management of the end application of hydrogen itself, right? Either it's going to be a fuel cell or it can be a different battery pack that is coming along with the components in an automotive industry as well. So we'll look into a cold plate study that that we can use for thermal management. Yeah. And also this session will especially include a live demonstration of SimScale on covering these three applications and what kind of first-hand insights you can get from these simulations. After the demonstration, we'll open up the stage to answer your questions, as my colleague Kanchan mentioned. So please feel free to use the chat option and ask your questions as we progress. Now, please allow me to explain quickly on how users can access SimScale at the first place and start simulating on the cloud native platform, right? As Kanchan mentioned, we are a truly cloud native simulation tool. And if you have a laptop or a PC in front of you with an internet connection, this is all you need to actually start simulating complex high fidelity simulations. So all you need to do is open up a browser and type in simscale.com, which will take you to the initial page of SimScale, where you can either log in if you already have the credentials, or start signing up for SimScale if you are a new user to SimScale. And once when you have your login, you can quickly jump onto the dashboard. So you can click on your credentials and jump onto the dashboard. And this is where you can see and all the projects that are available under your account. Right. The dashboard is where you can create, organize, or even share your projects within your team members. And if you have a team of, let's say, 5 to 6 people working on a same design or different designs, and you want to collaborate together, this is where you can create some organizational structures like creating team spaces, managing the users, and also adding new users as well to your account. Now let's jump into the tank filling case and explore what value you can get out of these simulations, either as a designer or as an engineer, right? So I'm quickly jumping on to the hydrogen tank filling case. For any tank filling case applications, like where it involves a highly dynamic gas like hydrogen, which is dependent on temperature and pressure around it, it is really important to understand the flow pattern. First of all, the temperature difference or the temperature distribution and the pressure dynamics inside the tank itself, right? This will allow us to design the components for the tank. For example, the kind of insulation you need, the kind of structures that can hold the tank while it is being filled as a part of storage or transportation, or even in an automotive sense, right? So these are some of the things that you can get out of simulation without doing expensive prototyping at the first hand. Let's imagine you are starting a project where you have an early stage conceptual design of a tank and the kind of inlet that you want to decide to fill in the tank, right? Generally, these tank filling procedures involve a pressure controlled inlet. So for example, on the screen, you see the cut section of a tank with an inlet here, and we're going to supply hydrogen into the tank. And as mentioned, generally it has like a predefined pressure ramp or a controlled pressure inlet using a device, right? That will be the input for the simulation as well here. And usually the amount of hydrogen that we can actually give into the tank depends upon the actual application, whether for automotive or transport or simply storage, and the actual capacity of the tank in terms of maximum pressure it can actually hold within the system. In our case, we have a tank that can hold up to around 77 liters of hydrogen, which also corresponds to about 35 megapascals of pressure that the tank can withhold. right? The first thing that you look at these kind of analysis is you want to find out a few things to make informed decisions. Like for example, if you're in a project where you need to decide what kind of insulation we need for the tank, the first thing you will notice is, or the first thing you will like to actually look into is the temperature distribution, right? When the tank starts filling in, you might see the hydrogen is coming in at certain temperature, which is about minus 15 degrees Celsius, which is pre-cooled. And once when it starts filling, due to the changes in the pressure and the flow, the tank and the gas which is present inside starts heating up. This is pretty typical for any hydrogen application. And you can actually see the dynamics of these temperature changes using these simulations. And the main end goal that you want to get out of this simulation is actually at the end of the fill cycle. Let's say we have the filling cycle of about 37 seconds, right? So right at the end of the fill cycle, the main parameters that you can extract from these kind of simulation is the temperature, either at the gas or at the skin of the tank itself, so that you can start thinking about the insulating materials that is required for these cases. Right, that's one of the typical value that you get out of these simulations. And apart from that, looking at the flow pattern will also allow us to optimize the filling efficiency. Let's quickly jump on to the variables and plot the velocity magnitude. And similar to what we have seen for the temperature, you can actually see how the gas behaves at each interval in the filling cycle, right? Initially, it starts with high velocity because the tank is empty. So you might see a different pattern where the tank is actually exerting pressure right at the center line of the tank. And then once when the gas starts filling up, you will see a decrease in the amount of hydrogen that is coming into the system. And then the pressure and the flow pattern tends to actually stabilize at the end of the fill cycle. This definitely differs depending upon the fill cycle time itself. With recent developments in the automotive industry and other hydrogen-based technologies, people are trying to actually see how fast we can fill into a tank, right, to save cost and time in such cases. So it's usually a good comparison if you have like 2 or 3 different filling times. For example, instead of 37 seconds, you want to actually fill it much faster, then you can quickly run a simulation and see how much rise in temperature you can expect from these changed inlet or supply speed. Right? Those are the typical results that you can get from these kind of simulations. And we should keep in mind the allowable pressure ranges that the tank is designed for. And with the flow pattern, you should be able to also see the pressure and the velocities at every point inside the domain as well. Right? This gives us some additional insights on whether we need to change the kind of nozzle that we want to use for the filling for this particular applications, or even the direction of the filling or the position of the nozzle itself in respect to the tank here. So these kind of design ideas can also be opened up when you actually do simulations on hydrogen tank filling case. Right. This also leads us to our second use case, which is about the kind of seals that is used for hydrogen technology. Right. For example, if you are dealing with such high pressure differences and also temperature differences, it's important that you need to actually take care of the safety concerns. In terms of sealing, you need to make sure there's no unintended leakage, and also if the sealing material can withhold these sort of changes in temperatures and pressures. And this takes us to the second use case, right? But before jumping on to that, I'll quickly again remind the audience that if you have any questions, please use our chat and ask the questions so that we can answer them at the end of this session. Yeah. And we're going to take a different direction, look into a structural analysis now, but let's quickly also see how we can set up a fluid flow simulation for a tank filling case within SimScale as well quickly, right? So just like any other simulation tool, the starting point is actually having the geometry. So SimScale is CAD agnostic for any CAD tool that you use or available in the market. So we support native file formats in terms of parts or assembly files as well. You can quickly drag and drop your CAD and you can start simulating on the CAD model. You do have certain options where you can edit your CAD. Let's say I have imported the whole model, but I just want to run a quick simulation. So I just want to do a symmetry, then I can do these kind of minimal CAD operations within the CAD mode itself. Once when the CAD is ready, all you need to do is quickly open up the analysis type page where you select the kind of physics that you want to simulate. As Kanchan mentioned, we are a broad physics simulation tool, meaning you can start simulating with a simple incompressible flow or flow around any baffles or objects, going into the heat transfer in a coupled way between your fluid and solid as well, using the conjugate heat transfer, or jump into the structural side of things where you can see load cases, different load cases, dynamic load cases as well, or thermomechanical simulations where temperature and mechanical strength actually are interlooped. Right. We recently also released the electromagnetics offering, which is in beta. So please feel free to actually open an account, start trying it out, and let us know if you have any questions. Apart from selecting the physics for this case, what SimScale does is it actually gives you a simulation tree, which can guide you in setting up the simulations, right? Let me quickly jump on to the tank simulation here. And here, all you need to do is set up the material that you want to use. For example, in our case, it's going to be hydrogen, and apply it to the volume here. After that, you can start setting up the boundary conditions, for example, the inlet. And then if you have a different case where you have an outlet as well or a relief pressure valve, then you can also use the pressure outlets as boundary conditions. And once when you have your materials and boundary conditions set, all the other steps are optional because it is highly automated in the background by SimScale. But if you have any specific conditions that you want to actually extract from the simulation or set up a specific mesh, then you can jump into that and start exploring that. Otherwise, you can directly start a simulation. And that's how easy it is to set up a simulation of these kind. All right, then it's time to jump on to the second analysis or the second use case, which talks about the seal or the sealing materials that is used in these hydrogen technologies, right? So for example, what we have here is a section of hydrogen seal of a tank. And the main objective of this is to actually see how the seal actually deforms with respect to the displacement or force that we provide, and whether this seal is prone to leakage or not. Those are the two main objectives of this simulation, right? So on the CAD model, what you have is a top plate, a bottom plate, and the seal itself at the middle. So this is a typical setup that you see from any sealing applications. It is not only relevant to hydrogen, but it can also be a different analysis where you want to actually see the leakage efficiency, right? So what we do here is like the first thing that we'd like to see is whether the seal can actually hold the strength and also stop the leakage, right? For this, what I'm going to do is simply plot the contact gap, which shows me the regions where it is completely in touch with the top and bottom plate, and also the regions where it is actually free to move, which will give a good sense of whether there's going to be a leakage or not. So on the top side here, you can see the color mapping corresponds to the contact gap, which means if it is closer to 0, it is actually in perfect contact with the other components of the sealing system. If you have like other gradients, let's say green or yellow or red, which means there is a gap in the sealing. right? For our case, we are technically looking to see if the seal is actually compressed enough and have this section of the seal as well as the second section here, which is perfectly in contact with the top plate. And you can definitely see these regions are blue in color, which means there is no or really less gap between the plate and the seal here. If I plot the seal here, plate here, you can see these are the regions which comes in touch with the top and the bottom plate. The second thing we would like to analyze is the actual shape of the seal itself, right? This will also give you insights about whether you can save material in these kind of sealings, or you need to add more material to make sure it is really safe for these hydrogen applications, right? So for this, I can quickly turn on the animation and see how the seal deforms with respect to the displacement or the force that we give. And at the final step where we have given the force here, you can see there are a lot more to improve. So um, the place where the seal is actually getting uh, sealed, sorry for that, can be actually modified to save material, for example, or you can actually start testing with a different shape of the seal to see if that improves the situation. So those are the main results you can get from these analysis. And on the quantitative side, you can also find out how much force you need to actually make the seal perfectly closed as well, right? If you have any questions on this one, we can definitely dive deeper into this application and see if you have a case where we can actually demonstrate on a one-to-one basis as well. Now, coming to the last application, which is pretty generic in terms of thermal management, right? So if you have any heat producing materials or process that is needed, you can actually think about the thermal management. For our case, what we are going to see here is a cold plate example. And here we're trying to actually apply the heat generated from a fuel cell and then see if the cold plate can handle this heat. And the main objective again is to keep the cold plate side at a critical temperature, below a critical temperature. And if we go over that, we can actually talk about how we can change the design and how efficient we can actually create these cold plates. For example, here on the screen, you have a serpentine flow cold plate where the flow comes in through one of the inlets. It passes through all these channels and then goes out on the other side. The idea here is to make as much as of contact to the plate which is closer to the fuel cell. Then we actually apply the coolant to take out the heat from the system. And here you can see the flow itself starts from here, goes into these channels, and then goes out of this. The key insights that you can get from these kind of simulation is whether you have any stagnation zones in your flow channel, or if there is air pockets or any other regions where you have low velocity, which will correspond to less heat dissipation as well. Right. For example, here the cold flow comes in, and then you can see at every corner you see a lot of blue regions, which means they are with low velocity. Either it can be a stagnation zone or can be a recirculating zone, which will affect the efficiency of the heat transfer itself. Right. On the overall side, what you can also see is the temperature distribution. So anything that is blue in color, which is around 20 degrees Celsius, and then the regions that you see in white are at least 25 degrees Celsius or beyond that, right? So most of the regions which is closer to the inlet is getting cooled, and once when the flow is actually reaching the end of the cold plate, it actually loses the ability to absorb heat from the material, which means it is not evenly cooling down the cold plate, which in turn will affect the longevity of the fuel cell, or in some cases like battery pack systems where you need almost an uniform distribution of temperature all through the battery cells, right? Otherwise, you might actually have one particular regions where it picks up the temperature and there might be some thermal runaway as well. So what you can do as a design engineer, so let's say we have this simulation from an expert. He has run the simulation, he has given it to me to actually analyze the results and come up with a new design for taking up more heat, right? I'll put on my design engineer cap now and see, hey, we have a simulation now. I have a second design that I want to test. So for example, instead of a serpentine cooling channel, I'm going to actually see if I can increase the heat transfer or the area at which the heat is getting transferred from the heat sources, right? So I simply removed all the channels. I put a simple cooling plate where the flow channel is almost empty, right? So the flow comes in, it actually tries to go out of the outflow through this particular narrow channel. And what I can simply do is open up the simulation that is being shared to me by an expert, duplicate, where I get a copy of all the settings, which is predefined, and simply jump onto the geometry and change the geometry to the new design that I have. Right, this way, I don't need to spend a lot of time in setting up the simulation, setting up the materials or the boundary conditions. I can simply start changing the geometry and starting the simulation right away. And the advantage of using a cloud native simulation tool is that you don't need to stop when you start one simulation. You don't need to wait for the simulation to finish this next one. All I can do is quickly go into the flow rate. Let's say I want to test it for different flow rates. I can start typing in a different flow rate, a lesser flow rate or a higher flow rate, start the second simulation. Also, what I can do is quickly jump onto the boundary condition and say, hey, I have a bunch of flow rates that I want to simulate. So instead of starting them one by one, I can use the parametric option where I can type in different flow rates or start bringing in a CSV file with a list of flow rates that I want to test. For example, let's go with 3 different flow rates for now and start applying that into the simulation. So right now we have started 3 different flow rates under an experiment, and previously we have also started 2 different simulations at the same time. So in total we are running 5 different simulations in parallel, and if one simulation is going to take certain amount of time, you can expect the results of other simulations as well within the same amount of time. So you can start comparing the results as well. All right, I hope this gives you a brief introduction about how to use the tool and how we can use these simulations to enhance the hydrogen supply chain components, for example, the sealing or the tank filling process or the thermal management. But at this point, I'll give a pause and also remind you that you can still put your questions onto the chat where we'll try to actually answer your questions right away. And thank you. And I'll hand it over to Kanchan as well so that we can pick up the questions and start answering.
Thank you, Ji. Thanks for a very detailed demonstration of different kinds of physics pertaining to use cases across that might be of interest to everybody. And so, yeah, I would now like to open the discussion for any questions. And we do have a few trickling in. And Adit, maybe this is something for you since you just showed the simulation for the tank filling problem. Is it possible to simulate this particular hydrogen problem with using real gas data?
That's a good question. So when it comes to hydrogen, as we all know, right, it is pretty dependent on the temperature and pressure environments around it. So it's important that we use the real gas, and within SimScale, you do have the option to switch between the material models. For example, here you can have an ideal gas simulation, but you can also turn on the compressibility, and then you can open up a few more options where you can import the real gas properties as well. Right, so changing the equation of state to real gas, you have the option to import your dynamic viscosity with respect to the temperature, density, and the specific enthalpy as well. I hope that answered the question.
Yeah, I think so. And how would you access this real gas table? That question is actually from my side because I think that would help understand better, like where could one get this real gas data from for
Definitely, yeah.
specific conditions?
Yeah. So usually there are a lot of databases available, but one such suggestion is the NIST database, where you can put in or plug in the pressure ranges and the temperature ranges that you want to simulate and get out the temperature dependent material properties, which you can upload that as a table format here.
Yeah. Okay. Thanks, Ajit. Let's move on to the next question, which is about whether we can do these simulations on the community plan. So I can start answering that, and please, Ajit, please jump in. Maybe for those of you who don't know, SimScale does have a freemium model where you can just sign up and start simulating immediately using our uh, a stack of free solvers. There are limitations, of course, in terms of the number of simulations that you can do and the core hours that you have access to. But a lot of this physics is available for you to try out on the community, except the subsonic solver where we did the tank storage problem. But there, if you are interested to take it to that level, and you can request a trial, and we'd be happy to set that up for you. And there's also a big resource of validation cases, documentation, and tutorials on simscale.com, which will help you get started on your community plan. Or should you choose to have access to our professional solvers like Subsonic and do really high-end simulations, then you will also have access to our support personnel through the chat option. And about the seals simulation that you showed, Ajit, I have this one specific question here. If these seals can be modeled with hyperelastic materials.
Yes. Once again, the material properties are really important for these kind of simulations or these kind of sealing applications, right? So definitely you can model hyperelastic materials within SimScale. And once if you have the material properties, all you need to do is go into the material section, and instead of the linear elastic material, which is set by default, you can change it to hyperelastic and then start plugging in your material properties. We do support a variety of hyperelastic models that you can use from. So depending upon the availability of the material properties, you can go ahead and choose one of the appropriate material models here.
Great. Thank you. Thank you, Ajit. And scrolling through the question, there is one specific question about CAD formats. I think you did cover that in the beginning of your the first case study, but maybe we can go over it again, like what CAD formats are supported, and generally like what maybe we can add on to it, like how much cleanup and all is required.
Yeah, definitely. That's again a good question. So um, within SimScale, you have the option to import native file formats from SolidWorks, Autodesk Inventor, Fusion, Rhino, CATIA, and uh, any CAD tool that you can name from the market, right? So all you need to do is write it up, export the CAD model, and drag and drop it here in the import geometry section. We also support generic formats like STEP, IGES, for example, STLs for certain applications as well. So if you have a CAD tool that can export one of the generic formats, or it actually comes under the native file formats, there shouldn't be an issue to actually drag and drop the geometries here. I hope that answers the question. And
Yes.
on the CAD requirements, it's similar to other tools, right? We do have a certain automation in the background which can handle certain level of details in the CAD, but this is typically specific to the use case. So if you have questions on whether you can simulate with the CAD CAD model you have, please feel free to actually contact us. We'll be happy to actually sit with you and see what is actually required in the CAD in terms of the CAD, or we can simulate it as it is.
Right. Thank you, Jeet. And we just have time for one final question. I think we've scheduled for about 45 minutes. So this is about a filtration system. Like if one wanted to model a filter within the simulation, what techniques would be possible? And again, I can start off here. So one way is to actually completely model the filter itself, like try to resolve it using the mesh. But typically that needs a very fine mesh resolution because you're looking at a few micron meters. So we do have capabilities to treat this filter like a pressure jump or like a porous medium in the simulation, and that's available with multiple of our solvers, be it the subsonic solver that you just saw or any of the open form based tool stack, which is also available on the community plan. So yeah, that would be the right approach to modeling the filtration systems. And I will now close off this webinar by, thank you all for joining us. Thank you for, giving us some of your time to listen to what SimScale is capable of with respect to hydrogen products and the hydrogen technologies. If you have any further questions, you can reach out to us on through our marketing email ID, or if you would like to set up a trial of SimScale for your specific problem, your specific simulation needs, please write to us at sales@simscale.com. Alternatively, you can go sign up at simscale.com, create an account, and start simulating immediately to get a flavor for what the simulation tool is capable of. Once again, thank you all and have a nice day.
Thank you all from my side as well. Have a nice day.